Welcome to The Explainer. Today, we're jumping right into an absolutely fascinating scientific journey. We're going to crack a 265-year-old cold case regarding the sun's magnetic field. And look, this isn't just some dry history lesson. We're diving into an astonishing piece of scientific detective work that actually managed to map out centuries of solar activity. And they did it using nothing more than centuries-old tallies of sunspots and some seriously cutting-edge physics. So let's get into it. Right off the bat, here's the massive dilemma we're looking at. Scientists desperately need centuries of magnetic data to really understand the complex cycles of the sun. But the problem is, modern observational tools, like the satellites we use to take direct, full-disk magnetograms, well, they've only been around for a few decades. So how on earth do you reconstruct a highly dynamic, immensely powerful magnetic field for periods of time when humanity barely had telescopes, let alone space-based sensors? Here is our roadmap for today's Explainer. We'll cover the solar time machine, clues from centuries past, building the sun simulator, perfecting the magnetic tilt, reconstructing 265 years, and finally, why this matters today. All right, part 1, the solar time machine. 265, that is the sheer volume of years we are talking about here, from 1755 all the way up to 2020. This research team successfully reconstructed the sun's surface magnetic field for a literal quarter of a millennium. That covers 24 complete back-to-back solar cycles, and they did it without having direct magnetic measurements for the vast majority of that time. To put that into perspective, our sun is roughly 4.6 billion years old. So even though we have about 50 years of absolutely fantastic, high-resolution direct magnetic observations, in solar time, that's barely a blink of an eye. It's just nowhere near enough data to truly grasp the long-term secular variations of the solar dynamo. If researchers want to predict future solar cycles and really understand long-term space weather, they realized they literally needed a time machine to look back much further. Which brings us to part 2, clues from centuries past. Look at the enormous gap in our timeline here. Astronomers officially started numbering solar cycles and systematically counting sunspots way back in 1755. We call that solar cycle 1. But humanity didn't actually obtain the first full-disk magnetographies until the 1950s. And systematic daily synoptic observations, those didn't become the norm until the 1970s. That leaves us with about 200 years where the only consistent data we have are just simple counts of spots on the sun's surface. So we have this crazy mismatch. On one hand, we've got modern magnetographies, super rich in direct data, but really short on history. On the other hand, we have the official historical sunspot record. It's really just a numerical tally, basically a line graph showing how many spots were visible month by month. Yet, incredibly, this simple historical tally was the sole clue scientists had to work with to build their continuous magnetic reconstruction. Let's look at how they did it in part 3, building the sun simulator. The fix for this dilemma is a pretty genius 2-part system. First up is SARG, the Synthetic Active Region Generator. SARG looks at the historical sunspot count for a specific month and basically invents plausible sunspots. It uses known statistical rules, things like how big spots usually are or what latitude they typically appear at during certain parts of a cycle to create these synthetic active regions. Then, it hands those spots over to the second part, AFT, the Advective Flux Transport model. Think of AFT as basically a weather simulator for the sun's surface. It takes SARG's spots and physically moves them around, simulating actual plasma flow, differential rotation, and diffusion. To get everything going, the simulation boots up in the year 1755 with a clean, perfectly stable dipole configuration. You can clearly see the distinct red and blue polarities sitting at the top and bottom. From this totally quiet starting state, they set the simulator in motion and just let 265 years of physics run its course. Moving right along to part 4, perfecting the magnetic tilt. Now, to keep this 265 years synthetic simulation from just drifting completely off the rails, researchers relied on a concept called active region tilt. Solar physicists often call this Joy's law. See, when sunspots emerge on the sun, they usually show up in pairs, a positive and a negative pole. But they don't emerge perfectly flat along the equator. They have a natural, predictable tilt to them. And it turns out this specific angle is basically the steering wheel for the entire solar cycle. Then there's the ADM, or axial dipole moment. To drop the jargon for a second, the ADM is simply the sun's global magnetic strength at its quietest time, the solar minimum. And why is that absolutely crucial? Because the strength of the ADM at solar minimum directly dictates how powerful the very next solar cycle is going to be. It's essentially the battery charging up the next cycle. So here is the real aha moment of the research. Through some brilliant deductive work, the team already knew how strong the historical sunspot cycles were. From that, they could mathematically estimate exactly what the ADM must have been at the end of each cycle to fuel the following one. So they ran their simulation, and if the ADM at the end of a cycle didn't match the historical expectation, they just went back and iteratively tweaked the tilt of the synthetic sunspots in SARG. By making tiny adjustments to that tilt angle, they perfectly matched the global magnetic buildup for all 24 cycles. And that leads us to the big reveal in Part 5, reconstructing 265 years. Check out the stark contrast between these two reconstructed maps. On the top, we have 1943, right during a solar minimum. It's quiet, and almost all of the strong magnetic field is safely sequestered at the poles. Then, on the bottom, you have 1950, a solar maximum. It's this chaotic, magnetically dense state with massive active regions just tearing across the equator. And remember, this incredible level of detail was generated using only a basic historical tally of sunspots as the starting point. And here is the absolute masterpiece of the whole project, the 265-year magnetic butterfly diagram. Time moves from left to right, covering 24 back-to-back solar cycles, and the vertical axis is the latitude on the sun. You can clearly see these gorgeous cascading chevron patterns, the butterfly wings, as sunspots emerge at mid-latitudes and migrate toward the equator, while all that leftover magnetic flux drifts up to the poles to reverse the sun's global field. It is a seamless, physics-based map of a quarter millennium of solar history. Now, I know what you're thinking. How accurate is this really? Well, to prove it, the scientists overlaid their purely synthetic model directly against actual modern satellite data for the recent cycles where we actually do have measurements. On the left is the synthetic simulation, and on the right is the actual data. Obviously, it can't predict the exact daily location of every random sunspot, but the large-scale behavior, the polar field strength, the timing of the reversals, the overall magnetic flux, it matches incredibly well. The model absolutely works. Finally, Part 6. Why this matters today. So why go through the immense headache of reconstructing the past? Well, because understanding a quarter millennium of the past is literally the only way we can safeguard our future. These magnetic maps power our long-term space weather forecasting, which is absolutely critical for protecting our modern satellites and power grids. They also help scientists accurately reconstruct total solar irradiance, basically how much energy the sun has been pumping into Earth's atmosphere over centuries, and not directly unlocks our understanding of the sun's role in long-term Earth climate variability, feeding vital historical data into really complex heliospheric models. I love this quote directly from the researchers. They state that these maps provide a physically consistent and observationally constrained view over 2 centuries. It's honestly a testament to human ingenuity. By understanding the statistical rules of the sun, researchers took a dusty historical ledger of counted spots and transformed it into a dynamic, flowing map of magnetic plasma. Which leaves us with a pretty thrilling question to ponder. If we can reliably uncover 265 years of the past using only simple tallies of spots and the laws of physics, what will these exact same models be able to predict for the next century of space weather? The solar cold case might be closed, but the future of solar forecasting is just bursting wide open. Thanks for hanging out with me for this explainer. Keep learning, keep questioning, and I'll catch you in the next one.